to last day of the school. I have a couple of announcements for tomorrow, especially. So tomorrow there will be a change in the program. So Chiara Caprini will teach at 2 p.m. tomorrow at the usual Q&A hour. And tomorrow is the last day. We are not going to have a Q&A, but the lecturers will have space either in the lectures or after the lectures to answer further questions that you may have. So Pedro, for instance, will have some time for questions tomorrow. Okay, so without further ado, Pedro will start his fourth lecture. Thank you, Pedro.
Okay, let me set this up. And can you all see my screen?
Yes.
Very good. All right, so we've entered this wilderness of constraining theories with data. And basically what I gave you yesterday was a summary. Well, I told you what we would constrain and what constraints we have. And I think what I presented yesterday is a pretty complete synopsis of where we are with attempts to constrain fifth forces on cosmological scales, or another way of putting it, deviations from general relativity on cosmological scales. But I'm not going to finish there, because I think what I've shown you is kind of the standard, what people are doing now, but things have to improve. And so I'm going to take the opportunity to discuss some things that are being done and have to be done so we can do this better. Okay. Now, one of the things that I flagged yesterday is this dependence on the parametrization when we go and do constraints. And one of the examples, I thought I showed an example which I think is a really good example of this, which is this plot. Let me just remind you what this plot is. In this plot, we are constraining on this axis, it's that mu over gamma, those two quasi-static parameters, and here it's sigma, all right? Look at, if you can see over here what I mean. And I'm choosing different time dependencies, and the different time dependencies I'm choosing are very simple, or they are choosing different time dependencies, the people who did the analysis. This is a Boss paper from 2017. This S can be equal to 0, which means that this thing is just a constant over time. Or this S can be 1, which means it's linear over time. So you have 1 and then there's this linear change over time. Or you can have it as S equals to 3, which means that it changes as a cubic. And depending on the time dependence that you assume, you get very different constraints on the on this parameter, on this mu over gamma or on this sigma. So your choice of time dependence, your choice of parameterization is crucial in constraining and using these methods to constrain deviations from general relativity. And the fact is, there are a lot of things we can parameterize. We can parameterize mu, gamma, and sigma, the quasi-static parameters. We can parameterize the alphas, the parameters in the Horndeski action, the scalar tensor action, and we have to parameterize the equation of state. Now, typically, what people do is they choose a parameterization with some constants, and they let those constants vary freely. But the question you might ask is, what are the physically allowed regions? In other words, you just pick some random function for these things. Do they actually correspond to a physically viable theory? They have to. We know, for example, in scalar tensor theories that they have to depend on the model for the scalar field. And in the scalar tensor theories, it's for the model of the scalar field. In other theories, it could be for a vector field, for something else. But they depend on something more fundamental. It's not just a random function that you put in, okay? And I'm going to give you an example of how this plays out. I'm going to consider one of the simplest examples where we were able to work this out in detail. Take quintessence, right? If you remember in my very first lecture, I said, you could replace the cosmological constant by a scalar field with a potential. This is normally called quintessence. And that scalar field will have a kinetic energy and a potential energy. We can pick a potential. Now let's pick a big subclass of these quintessence models. Let's pick a subclass where the scalar field is basically frozen at very early times and only starts rolling at late times. This is known as thawing quintessence, okay? And let's look at the standard parametrization for the equation of states for this theory. And let me remind you, the equation of state is nothing more than the kinetic energy minus the potential energy. That's the pressure over the kinetic energy plus the potential energy. That's the energy density. This is P over rho, okay? That's the equation of state. And so in principle, you look at a model, it tells you how phi evolves, and you work out the equation of state. But as I pointed out earlier, there's a pretty simple parametrization that seems to work quite well, which is just to consider a constant and then a part which is linear in 1 over A. And what people normally do is they say, let's study quintessence. We need an equation of state. Let's assume this parametrization, and then let's just take uniform priors, pick uniform priors over W0 and WA. Just take these WA, this W0 and WA are completely free constants, and we can pick whatever they are. And so let's just find the best fit. And you do that, and this is the kind of constraints you get. Okay, this is W0 and this is WA. And as the data gets better, it gets tighter and tighter, and it's mostly focused around -1 and 0. -1 for W0 and A at 0. Although it's slightly pushed to negative values of less than -1 values of W0. Okay. But you might ask yourself, but where does theory lie on this? Suppose you were to consider what quintessence really is, which is a theory of a scalar field. Where does the equation of state in these variables lie on here? Could it be anywhere? Is it localized over here? Is it localized over here? Is it a strip that goes in this direction? Is it a strip in that direction? And kind of the analogy to think about, and you may have seen this in the CMB, is when we look at the CMB, we often parameterize, two of the parameters we look at are the spectral scalar index, NS, and the tensor to scalar ratio, R, okay? And when we do data analysis, we let R and NS to vary freely, okay? And we get these contours. But then what we do is we look at models and we see where do models lie relative to these contours. And we know that, models with single scalar fields, we know that concave models where the potential is concave lie down here, that models with convex potentials lie up here, phi squared lies up here, so it's already in tension with these constraints. Linear in phi lies within. In other words, different models will lie in different regions of this space. So you can ask the same questions about quintessence. Now, the first thing you'll notice, we do know something about this. We know that thawing models, remember that thawing models are models where phi dot starts at 0 and evolves away from 0. That if you look at where they lie in the, my mouse doesn't seem to be working, where they lie in the W0 WA plane, they lie more or less around here in this part. Okay, so you already know that they lie in a wedge, but we can do better than that. We can sit down and we can just write down all the thawing scalar field models we know and assume reasonable values for the parameters in the potential for everything else, under some effective field theory principle, naturalist principle, whatever you want, and you do that, and this is what you get. Okay, what you get is that if you look at the theories and look at the W0 WA plane, you get that actually the theories lie on a very well-defined track in the W0 and WA plane. So this is what theory is telling you. Theory is telling you that you can't just vary W0 and WA arbitrarily if you're looking at thawing quintessence. You have to vary them within certain constraints. And this is what you get if you have a potential where it's just a monomial. If you construct a potential which is more, but you construct it using the principles of effective field theory. If you construct potentials which arise from, for example, more string theory motivations, they all seem to lie more or less in the same region, which is quite fascinating. Okay, and where does that lie relative to data? Well, what this here is a forecast. No, it's actually current data. Okay, this is current constraints on W0 WA, assuming uniform prior on these quantities. And these here are the priors, the theoretical priors. And what you see is that they actually aren't aligned with this. They're kind of orthogonal. So if you were to actually assume physical priors for your thorium quintessence model, you'd find that actually your constraints are much tighter than what you're considering here. This region is just uninteresting. It's not physical. The physical priors lie over here, and your data is telling you that it's constrained to be over here. So this is something you really have to bear in mind when you're trying to constrain these parameters that we introduced for extensions of the LambdaCDM model. Now you can, I'm just going to give you kind of a work in progress just to show you that you can go further than this. If you want to, this was for quintessence, but we're really interested in Horndeski models, and Horndeski models have many more parameters. But you can decide to restrict yourself to a subclass of Horndeski models. And so suppose you restrict yourselves to shift symmetric models. That is models where you can transform phi by a constant, okay? And you can just use effective field theory arguments to write down the most general action of this form. And what you find is that you basically have 4 terms. You have this term, and then this term and this term, and you have these constants over here, okay? Now, suppose that you all right, so this is your model space, okay? Well, the first thing you want to see is what Horndeski parameters do you need to worry about? You need to worry about the equation of state, and you need to worry about the the equation of state. And in principle, you need to consider the 4 other Horndeski parameters, the 4 other alphas. But what you find is actually alpha m and alpha t are equal to 0. And the only 2 that are important are alpha b and alpha k. And it turns out that alpha k is completely unconstrainable by large-scale structure. So the only one that you need to worry about is alpha b, okay? So that's the first thing. So you only need to worry about 2 parameters, w, the equation of state, and alpha b. But now we can parameterize these 2 things. And we already know that w is well parameterized by this. And I show this because you can see that in some regimes it looks like it fits beautifully. In other regimes it doesn't look great. But it turns out that this fit is good enough in terms of observables. In terms of observables, this is the accuracy that you get is well within what we need for current and future surveys. But with alpha b, it's much more interesting. What you find is you could imagine that alpha b could take any function, but it doesn't. In this class of models, it's simply some constant times some inverse dependence on the Hubble rate to some exponent. And so that only depends on these 2 constants here, alpha b hat and m. So by looking at the theories and exploring how they evolve, you realize that the priors are much more restricted than if you just applied these blanket uniform priors for any constants that you came up with. And this is what happens. This is an example of the constraints that you might get. Let's just focus on this panel over here. This is the alpha b and alpha m. These are the alpha b and alpha m that parameterize the alpha b parameter. This is W0 and WA. And what you have here is you have the data is in gray, the priors are in green, and you get the combination. And what you get is you get incredibly tight constraints. You get incredibly tight constraints because you are assuming physical priors, okay? Now, this is a completely open field. People are only beginning now to realize that if we're actually going to get interesting constraints in physical models, we need to start thinking about where, in terms of observables, these models lie. And this is one approach to doing this. But there's more to this. And just to end this discussion about data, I'm going to show you where we're about to get these incredible data sets, and we need to make sure about how well we constrain these extensions to general relativity. And so I just listed a number of aspects here that really one has to worry about. One can't do this randomly. One has to be careful about multiple aspects. And so I've written here what you need to do if you want to test extensions of general relativity. I mean, the first thing is kind of essential is you need to have a little bit of an analytic understanding of the evolution of what's going on. You know, you code it up, you see what's happening, but it's important to understand why things are evolving the way they are and in what way they are different from what you expect from general relativity. You also need to have accurate implementation of not only the evolution, the background evolution, but also the linear perturbations, the stuff that you were learning about with the other teachers on this course. And there are codes that do this. There's EFT-CAM and high class. There are others There's actually a list of quite a lot of codes that do this, but you need to have this, and you need to be sure that they're accurate. If you need to find some way of calibrating and know that these codes are correct. Another aspect which is really important is if you're really going to take the maximum constraints from your data, you need to try and harness as much of the power spectrum as possible, and that means trying to go into the nonlinear regime. So it's important to have a good and accurate model for nonlinearities. One of the things that we've learned over the years is that it's not only enough to have models of the nonlinearities, there's all this other stuff going on. You have galaxies when they form, they have supernova, they have active galactic nuclei. All these lead to incredibly nonlinear processes that push gas out and affect the matter distribution. So you need to be able to model what are known as baryonic effects somehow. And if not model them, at least to be able to marginalize over them. Another important aspect is what you'll find is that different models will have different degeneracies with parameters that we know. In other words, you may find that your parameter in your new model will have a degeneracy with parameters like the helium fraction or the matter density or other things. And finally, we need to understand priors, and we've already mentioned this. And so I'm just going to show you an example of this for the simplest. I always go back to this theory, the simplest case, Jordan-Brans-Dicke. Okay. We go back to Jordan-Brans-Dicke. Remember Jordan-Brans-Dicke? It was simply phi times an r here. I've now pulled out the Planck mass just to make it dimensionless. Phi times an r here. Then we have the kinetic term. We have a potential. I put in a potential here, and a minimal coupling to matter. Okay. And when I talk about analytics, it's, for example, you can actually solve this in the matter regime and find an exact solution for the scale factor. And what you find is that the scale factor, instead of going as t to the 2/3, will depend on your omega parameter. I've dropped the BD here, but you see what I'm doing here. The scalar field also in this regime, you know how it evolves. It goes as 1/1 plus the parameter that you have in this model, this single dimensionless parameter. What you care about is your observables. And so what I have here is deviations of the angular diameter distance from general relativity. And what you find is it depends on 1 over this parameter W, and there's some function of Z, which is not important. But the key thing is if this W goes to infinity, this goes to 0, and so we recover GR. The same thing about the growth rate. It depends on 1 over W, and as W goes to infinity, which is the GR limit, this goes to 0. Okay. And so this is what I mean. You can work out the analytics of this model quite well. And this is just plots of exactly how these things, how the angular diameter distance and the growth rates depend on changing these parameters. This is the point about this is that you code it up. You have to put it into your Einstein-Boltzmann solver and get accurate results out. Now, this is an interesting plot because this shows what happens if you start exploring how things depend on all the parameters, okay? And what you find in this case, for example, is there is a very tight constraint between the helium mass fraction and the Jordan-Brans-Dicke parameters. In fact, this is just to show you what happens in the EE polarization. You can construct two models with very different values of the helium fraction and the mass and the Jordan-Brans-Dicke, and they look exactly equivalent. So you have to keep an eye on this, because one of the things that you will realize is this will introduce extra uncertainty in your estimates of deviations from general relativity, but it'll also enlarge your error bars on parameters that you thought you had very tightly constrained. So you might assume a value for YP, and then you'll realize that actually I'm not allowed to assume that because that's degenerate with the parameters that I'm looking at. This is what happens. This is what you have to do, for example, if you want to start including the linear regime, the nonlinear regime. This is the power spectrum over here. This is the wave number. This dashed curve is the linear power spectrum. And this is what you get. The crosses are what you get if you, the crosses is what you get if you use n-body simulations to try and study what happens to Jordan-Brans-Dicke theory, and you see the nonlinear correction, and you see as you start to move away from here, you need to start considering nonlinear corrections. And so one of the things you need to do is you need to come up with a model for this, and we have actually done that. And the only point about this is this shows that we've constructed an analytic model which when you compare to the new n-body simulations are accurate to within 5%. We will have to do better for future data sets, but you know, this is where we are now. This is what happens if you choose different priors. So this is the Brans-Dicke parameter, and you can choose uniform prior here on log of the Brans-Dicke parameter. You can choose uniform prior on the log of 1 plus 1 over the Brans-Dicke parameter. You choose a uniform prior over 1 over the Brans-Dicke parameter, or the log. I mean, you could choose, and all of these will give you different results. So you have to try and figure out what is the robust set of priors. And you may find that your results will always depend on the priors, but you do need to know this. Finally, the fact that you choose different priors will affect your other results. So again, this is the choice of different priors here. And so I've written here the different priors on the Brans-Dicke parameter. And this is a plot which has on the y-axis, you have the neutrino mass. And on the x-axis, you basically have one parameter, which is parametrizing the amount of baryon feedback. Okay, one of the things that I mentioned. And you see very different curves depending what prior you choose. So the point is all of these things play into each other, and you really need to understand them very well to know that when you make a statement that we've constrained this theory or general relativity to this precision, you know what you're saying and how this is affected by other things. I'm not going to go into this, and I'm not going to go into this either. So let me just summarize. So this was kind of a meaty lecture which started yesterday and ended today, and it's that I still have another bit that I'm going to talk about, but in terms of very large scales, it's now possible to constrain gravity with large scale structure. I mean, when we now have weak lensing, we have measurements of the growth rate, we have measurements of the angular diameter distance. It's possible to use these things to constrain general relativity. And the general approach, which is what people are doing, is that you find a way of parametrizing linear perturbations on very large scales, okay? And you parametrize them and you constrain those things. When you do that, what you find at the moment is there is some small inconsistency. There's some evidence for deviations, but this evidence for deviations you can trace to a problem I see, or I wouldn't call it a problem, an interesting thing that's happening in the Planck data. So at the moment, it can all be traced to what I call the AL problem in the Planck data. But this is really just the beginning. You know, we need to understand the AL, but we need to do better. We need to understand priors much better. And we've kind of been oblivious to priors, but we need to understand priors to understand if our theories are even consistent with the data or if the constraints are tighter than we thought. And we need to start watching out for a number of things. We need to have precision linear methods which are precise calculating the linear perturbations. We need to have methods to calculate nonlinear corrections. We need to take into account baryons, degeneracies, and the priors. There are a number of things that you now need to worry about. We can't just generate a model with CAM, fit the data, and be happy with it. I think we now need to be much more precise in what we do. Okay, so I'm going to stop this bit now, and I'm going to take questions. Let me stop sharing. I've stopped sharing. And I'm going to go to the chat. Is a prior a way to parameterize the model? I think that's a very good way of putting it. In some sense, it is a way to parameterize the model. In other words, when we say we're parameterizing a model, we sometimes stop halfway to writing down what the parameterization is. And writing down a parameterization, you know, you may have some constants in that parameterization. We also have to say what values those constants are allowed to have. So I think it's a very good way of saying that. It's a prior is a way to parameterize the model. Next question from Nelson Ferreira. Are some probes, in other words, weak lensing, CMB, galaxy clustering, intrinsically better than others to constrain gravity? I think they are. I mean, it depends on how the models evolve. But I think, for example, as a general well, it's complicated. I was going to say that as a general principle, weak lensing and galaxy clustering, because galaxy clustering probes the growth rate, are better than the CMB at constraining gravity, okay? But that is assuming that most of the effects or most of the deviations from gravity happen at late times, okay? And I'm going to give you a counterexample. Counterexample is Jordan-Brans-Dicke. It turns out that Jordan-Brans-Dicke is always away from general relativity at all point in its history. And if that's the situation, it will affect the CMB, and it'll affect the CMB until now. So in that sense, then the CMB will be much more powerful than just galaxy clustering and the growth rate. And indeed, we do find that with Jordan-Brans-Dicke, the tightest constraints at the moment come from the CMB on large scales. What about constraining gravity with the bias parameters? Beatrice Tucci asked that. It's a good question. I've never thought about that. I would think that that might be complicated. That might be difficult because of I mean, the bias in some sense encapsulates all that other stuff which is messy and which we don't completely understand. Although there are, you know, more and more kind of analytic methods for doing that. It's a really interesting question. I don't know how to give you a good answer to that, but I like that question. Reggie, if we are going to start with specific models and integrating the Boltzmann equations derived from them, where does this put the arbitrary EFT functions then, e.g. braiding? Well, but so Reggie is asking a question, which is often when you use the codes like EFT-CAM, you have these free functions. And he's asking, what do we do with these free functions if we're looking at specific models? Well, the fact is, these free functions are something very specific when we look at specific models. In other words, for example, for Brans-Dicke, we know exactly what alpha m is, or we know exactly what alpha k is. So these are only free functions because we're making no assumptions about where they come from. If we start making assumptions about where they come from, they will give them very specific functional forms. Okay. Any more questions? I wouldn't mind you asking me more questions, because if not, I'm going to start on my last topic, which is quite different. Well, no, I've still got something. Yeah, I've still got another bit slightly related to this to talk about. But okay, well, let me talk about the next thing. And the next thing is going to be quite quick, but I think quite important. All right. My mouse is not behaving very well. Okay, no. Now, I've been talking about large scales, right? Large scale structure. But I mentioned that there's a question here from Tibor Dome saying, is WBD related to the W of dark energy? No. WBD is the parameter, that parameter in the kinetic term of Jordan-Brans-Dicke, okay? It's not the equation of state, right? I'm not going to answer any more questions there. Now, let me get this. I need to share screen. Okay, I hope you can see this. All right. Unfortunately, I'm not where I want to be. There we go. Okay, good. So I'm going to start talking about something which I'm going to talk briefly about something which I think is one of the ways to the future and one of the ways of moving forward in all this. And it's the following. We've focused on large scales, what we call summary statistics, power spectrum, correlation functions, etc. And when you do that, basically, for example, in a galaxy survey, you don't care what galaxies are. Galaxies are simply these test particles that live on space-time and are distributed, and they form this cosmic web, and they cluster gravitationally. But you're not really at all interested in the details about galaxies. You use them as simply as beacons. It's the same thing when we do weak lensing. When we do weak lensing, they're just points of light. They're sources of light with at good positions in the sky, right? And the cosmic microwave background, it's just photons streaming through. And what we do is we get these kind of images, and these images where we don't care about the detail, the kind of the building blocks of these images. We just care about the image, and we analyze them statistically. Okay. But we know In other words, galaxies are dots. But you could have a different perspective, right? You can think that we now have catalogs with millions of galaxies, right? And these millions of galaxies, each galaxy is an entity in its own right, has its own structure, its own behavior. And you could think, well, instead of just ignoring that galaxies are galaxies, why not look at them as galaxies and use them as laboratories to look at how their structure depends on environment? And so this, I think, is a field which I think needs to grow and in some sense explode, which is we should start thinking about using galaxies as laboratories for fundamental physics. Now, let's just build a cartoon model of what a galaxy is, right? A cartoon model of what a galaxy is we believe that there are these halos, okay? These are halos of dark matter, these kind of spheres. We believe that there are stars and that the stars live in a disk and in a bulge, okay? And surrounding this disk and bulge, there's gas, okay? And at the center, there's often a black hole. So this is a kind of very simplified model of what a galaxy looks like. But we know that actually galaxies are very diverse. So this is a kind of a rogues gallery of a bunch of galaxies from the Sloan Digital Sky Survey. And, you know, while they all look similar in that they're a blob of light, structurally, they're all very different. You know, their spiral arms are different. Some aren't spirals, some are more deformed. You know, there's a lot going on with each individual galaxy, okay? In fact, if you look at the Milky Way, it really is a highly complex structure, right? It has these spiral arms. You know, we live around here, has these spiral arms. If you look at it in different frequencies, this is in the radio continuum, you see all this stuff going on from supernovae that have exploded. You have shells in the radio. This is one of the most amazing pictures. This is a picture at the center of our galaxy by the Meerkat, the Meerkat telescope in South Africa, a radio receiver. And you see the strands due to the magnetic fields. Galaxies are these incredibly rich objects, okay? Now, you can look at them and you can think two ways. You can look at these images and you can think two ways. You can think, oh my God, there's no way we can use these objects to do anything fundamental, right? There's just too much physics going on. It's just, they're too complex. We don't really even know how they form. We have some ideas, but we don't know in detail how they form. Before we understand how they form, we shouldn't really be using them for anything, okay? But the other alternative is, well, yes, on the other hand, we have lots and lots and lots and lots and lots of images of these galaxies. And we are getting very detailed images of these galaxies. The galaxies is a completely unprobed regime for gravity or for fifth forces. And furthermore, okay, we have these uncertainties. Well, let's just factor in the uncertainties. Let's factor in the uncertainties and see where we go. And if the uncertainties are large enough, okay, we give up. But they might not be large enough. And I'm going to show you that at the moment, they don't seem to be large enough. So what's the quest? The quest is to try and look for evidence of fifth force. And that, remember when we spoke about screening, we have the fifth force. You know, a fifth force has an amplitude and a range. These things can depend on the environment if the system is screened. So one of the things you can do is look at galaxies and their constituents in different environments. In other words, you can look at galaxies which live in voids and compare them to what they're doing if they live in clusters. For example, you could look at stars which are screened because they're compact enough to be screened versus gas and dark matter, which in principle aren't screened. You can look at black holes, which won't be screened because black holes obey a series of properties which don't allow them to be screened versus stars that can be screened. So you have these differences in these objects, and can you use that information to do something? Well, the first thing you've got to do is you've got to build a map of the environment. In other words, you want to look at these objects in different environments. But so to do that, you have to have a very clear idea around us of how the environment changes. And you can do that. And Harry Desmond has done that with incredible care. Basically, what he's done is he's taken a full sky survey of galaxies, okay, and what he does is he looks at each of these galaxies and he assumes that these galaxies are associated to halos, so he can try and reconstruct the gravitational potential on small scales. And then on very large scales, you can build the long wavelengths using constrained realizations, given the information he has of the environment on larger scales. So in doing that, he can basically construct a gravitational map from the very large scales to the very small scales. And when I say the very large scales, at the moment, this is out to about 200, between 100 and about 200 megaparsecs, okay? And these are examples. This is a map of the gravitational potential, a slice, a two-dimensional slice through a part of our local volume of the gravitational potential. This here is the acceleration, so the gradient of phi. This is the curvature. And so you can imagine seeing what happens to objects if they're here versus they're here. You look for galaxies and see what's happening to them over here and seeing what's happening to over there and see if they look different, because if they are different, that may be the evidence for something, okay? So what are you going to look for? I'm going to give you three examples, actually. The first thing I'm going to look for is offsets. So imagine you've got a galaxy, and this galaxy is in an unscreened region. So you go in a region where the fifth force is unscreened. And then you have that this galaxy is made of a halo, gas, and stars. Now, the halo and the gas are also unscreened, which they'll feel this fifth force, while stars are screened because they're compact, so they won't feel this fifth force. So the halo and the gas will feel a force that the stars won't feel, which means that the stars will be slightly shifted relative to the gas and halo, okay? So what you have is that the unscreened part, the halo and the gas, will have some external gravitational field, and then it'll feel that this has a typo, and I'm going to update the transparencies on the website, but there shouldn't be a delta here. It's delta G over G times the fifth force. So they'll feel a fifth force acceleration here, while the stars won't feel that. But because you've dislocated the halo and the gas relative to the stars, you've dislocated the center of gravity of the system relative to the stars. So the stars will feel a pullback due to that gravity. And so what you have is that the stars will be in equilibrium, slightly offset from the gas, okay? And what you can go and do is you can look for that offset. And you know that in unscreened regions, sorry, this is the wrong way around. In unscreened regions, should be unscreened here, this will be, you'll see a slight shift. But in screened regions, there will be no shift, okay? And so you can do that, and you do that, and you pick a catalog, and you go and look for galaxies which are in unscreened regions, and look for galaxies which are in screened regions, and you look at the offsets. And this is exactly this exercise. This is something that we did a few times. This is the latest result. And so this is a constraint on delta G over G, so the strength of the fifth force, as a function of the screening scale. And what you find is that you can get incredibly tight constraints on the strength of the fifth force in this way, all right? And this is just using galaxies as laboratories, okay? And you can go a step further, and the step further is, here we're just considering the kind of the bulk separation of the stars from the bulk separation of the disk of stars from the gas. But you can go further. You can look at how the stellar disk itself is deformed by the fifth force. And the fifth force will deform the stellar disk because the fifth force has a certain direction. And so if the fifth force is in a direction orthogonal to the plane, it'll deform that disk, okay? And you can work out how strong that deformation is. This is the deformation of the disk. Z is basically the direction perpendicular to the plane of the galaxy, and it'll depend on the distance from the center of the galaxy, and that gives a warp. And so you can go away and look at warps. And this is just the example of one particular galaxy. This is the warp of one particular galaxy, and this is how you view it in a different way. So you can look at warps of galaxies. And again, you can see if galaxies are warped in a certain way, aligned with the fifth force or not in different regimes. And you do that. And again, you find incredibly tight constraints, okay? And what you find is you get constraints depending on the screening scale, which are as low as 10 to the minus 4. So the point about this is an incredibly powerful way of constraining fifth forces. And what we find is that even including the uncertainties we have in the baryon physics, the uncertainties we can look at numerical simulations, and we've been doing that now. They are within the same errors as the statistical errors this far. So these really are powerful constraints. The final thing I want to show you is what happens, what does this mean? And this goes back to the question that I've been asked again and again of why am I telling people not to work on F of R? I don't think people should work on F of R, because if you use this test and you apply it to F of R, what you find is that F of R naught, i.e. the derivative of F by R today, is less than 10 to the minus 8, which means it's completely negligible. For F of R to have any cosmological significance, you need it to be of order 10 to the minus 5, maybe 10 to the minus 6, but really 10 to the minus 5. And we're saying that with galaxies, we're already showing that if there is F of R in the universe, it's less than 10 to the minus 8. So it has no astrophysical or cosmological significance. So this is the key point why I'm saying you might want to learn of F of R for historical reasons. A lot of people will carry on writing papers about F of R. I think F of R should be put to rest. Finally, that used chameleon screening. But what about Weinstein screening? Well, it turns out that, remember what Weinstein screening appears in Galilean models. Galilean models have this symmetry that I showed you. And in Weinstein screening, it turns out that black holes are unscreened. And the reason black holes are unscreened is because they obey what are known as no-hair theorems. It's something I will come back to in the next lecture. And so black holes are unscreened, but stars are screened, which means, again, you're going to get an offset between stars and black holes. And you can work out what that offset, you can work out what the fifth force is. And the fifth force in this case is going to be depend on the scalar charge. And in this case, it's going to be the integral of the density of the stars. That gives you what that is over there. You have this amplitude, the delta G over G, and you have the Weinstein radius here. So too close to an object, this is suppressed, but outside it's not. Okay. So you can do this exercise. You can, first of all, you look for regions which are screened or not screened. And then what you need to do is you look for offsets. And this is an interesting exercise because this is something that people actually do, but they don't really know what to do with. So there are a number of papers, and these are a list of surveys which have worked out the offset of the central black hole in a galaxy. And what you find is this redshift dependence. This is the offset, basically. And this is the physical offset, and you find this redshift dependence. And most of this redshift dependence is only attributable to resolution. And this is the statement that the further away an object is, the harder it is to resolve. So you get this trend in the offset. It's not at all clear that this is anything physical at all. Okay, but there is data out there. Well, if you take this data, you can go and analyze it. And this is an example of how you can do it. So you need to build a model for these offsets. And what one finds is that the simplest model is a combination of a Gaussian and a Laplace distribution. So delta theta is the angular offset. This is the variance in that angular offset. We have here F, which is how much that distribution is described by a Gaussian and how much is it described by a Laplace distribution. This is the Laplace distribution. And this is the variance in the Laplace distribution. And you do that, and you build your model, and you can constrain your delta G over G in this theory. And what you find is that your delta G over G is of order 0.1. So you can find an upper limit on screening in these forces of about 0.1. Okay. So this is really the beginning of the field. Okay, this is the beginning of a field where you start using these objects, you think about the details of these objects, and you start placing constraints on fundamental physics. You can do this for other things, for dark matter, and I've written some papers on dark matter, and I think other people are working on that. And there's a whole report on this, which is I put in the references somewhere in the transparencies, on where you can see what kind of new physics you might do on these astrophysical scales. So let me just finish this bit by saying that galaxies have a tremendous potential for constraining fundamental physics, and I really believe this. And I think the reason many people don't do this is because they're very, very messy and they're very challenging. But for those of you who have an interest in statistics, I think this is at the vanguard of the kind of thing that you might be interested in looking at, because it must have wider applicability. And the way I describe this is the type of things that you need to do is you need to construct messy Bayesian forward modeling. In other words, you need to be able to construct a model, a Bayesian forward model, which includes aspects that you don't fully understand, and you have to construct a model for those aspects that you don't fully understand, based on what you know from theory, but primarily from the data. Okay, and if you're able to do that, you will be able to get faithful results. And then the question is, will those reliable results, and will those reliable results be constraining? Well, you have to wait and see. We found that they've been very constraining in the case of F of R. And in the case of Galilean, you know, it's strong enough. It's not comparable to what we're getting in the chameleon case, but it's, you know, it's still very competitive with other constraints. Very good. So I'm going to end this section here, and I'm going to end today's lecture here because I don't want to start tomorrow's topic today, but I'm open for questions. Right, I can see. Very good. Right, halos, Oscar Castillo, Felisola, halos and gas behave differently than stars. What impact have that fact interpretation of the observations of the bullet cluster? Well, I think what you're saying here is we need to be careful with the what would people call the gastrophysics, and that's what I call the messy aspect of the modeling. And I completely agree with you. And the way you do that is twofold. You make sure that your model is robust enough, but also you try and see in numerical simulations and understand the systems generally as best we can. Are all models with chameleon screening excluded together with F of R? The good question, I'm not sure. And I've got to be very clear, I'm excluding who's a wiki F of R, a particular type of F of R, but which is the only model of F of R that people are studying. Could this offset black hole unscreened nature be seen in gravity waves from black hole, or by a black hole neutron star merger? No, not the offsets. No, that couldn't be seen. There might be other effects that could be seen. And I think it's a topic that people are looking at in detail who are studying compact objects. Why are black holes unscreened? Very good question by David Gutierrez. There's a series of theorems that I will talk a little bit about this in the next lecture, but in a nutshell, there's a series of theorems in general relativity that black holes only have no hair. In other words, you can't glue scalar fields to them in any fundamental way. It turns out that Galilean theories also have that problem, which means that you can't construct a non-trivial profile for the scalar field so that it behaves as a screened theory. So that's the basic answer. Could you please remind us the difference between Weinstein? No, Weinstein and Galilean screening is the same thing. I think that was the point that I was making in that transparency. How do your constraints on F of R depend on the functional form, aka the specific and parameters within that theory that you choose? Very good question. This was Mariana asked this. It's very much who's a wiki. This is for who's a wiki. There hasn't been any work on other theories, a substantial work on other F of R models for cosmology. My hunch is that if someone comes with an F of R theory, it's very easy for us to work out how our constraints translate for them. I think they're going to be in trouble, but that's just a hunch. Reggie is asking a question. Perhaps you will talk about this tomorrow, but can you tease what offset you were talking about, stars and black holes? What I mean is that when you have a black hole, you have the disk and you have the black hole. And in principle, you expect the black hole through dynamical friction to have ended up at the center of the galaxy, but actually it's slightly away from the center of the galaxy. That's what I mean by the offset. What about the difference of screening of neutron stars and black holes? This is Zakaria asked this question. Really good question. So that's a completely open question that people are beginning to look at now. For example, you can imagine neutron stars in Galilean theories are screened and they orbit each other and they form a black hole, and that screening scale has to go away. How does that process happen? So very good question. How does that screening, how does the screen neutron stars involve an in-spiral, and how does that deform the orbits and the production of gravitational waves? Very good question. Are there hydrodynamical numerical simulations that also resolve? So Beatrice Tucci asked this. Are there hydrodynamical numerical simulations that also resolve the physics of galaxies with modified gravity? Excellent question. There are first attempts at this. There are first attempts at basically modifying some of the main codes like Ramsys and adding in modifications and see how that affects things. So yes, the answer is yes. Is this the only constraint to rule out f of r? I think there are other constraints. They're not as tight as this. So this was a question by Zakaria. Okay, any more questions? Okay, Haris Serafos. I don't understand how the offset effect from modifications to gravity can be differentiated from the gravity of dark matter effect. I don't understand your question. What is the gravity of dark matter effect? Gravity of dark matter effect is simply gravity. And so if you've got a fifth force acting on, your gas, which isn't acting in your stars, it's going to be distinguished from any force, from the gravitational force. Any more questions?
Well, I have a question.
Yes.
So the fifth force is always universal, because I've seen papers where people say, okay, only fifth force between dark matter.
Very nice. Yeah, very nice. So I'm looking at universal fifth forces here. And so yeah, I think you're really raising a key point, which is you have to think about all the possible different regimes. Okay, and so you could, I'm talking about universal fifth forces. You can often translate these constraints on species dependent couplings. So the kind of thing that you're talking about, right? Some force that couples to one thing and doesn't couple to another. You can translate these constraints onto that as well. And so the way that you translate these constraints will depend on the scenario that you're looking at. But I'm sure it's applicable. I know it's applicable to the kind of thing you're asking.
Raul has a question.
Hi, Pedro. So you seem to be very excited with galaxies. We barely understand halos, but it is true that halos, we can't really observe much from them. We are still trying to understand how, properties of halos, how they inherit the interactions and so on, how they come from initial conditions and so on and so forth. Galaxies are much more messy, but I guess it's a matter of what you believe is the future. In that sense, you believe that galaxies, despite the fact that they are these crazy messy situations, these mixes of everything, that because we are observing them in huge numbers and much more detail, that there is the opportunity there to learn something. So this is kind of how your nose is, what is your nose is telling you?
There are two aspects to this. So so what I'm really saying is there are two attitudes. One attitude is they're messy, and you just give up, okay? The other attitude is they're messy, but in the real world, we model messy systems often, okay? And often we don't need to know the exact details of the messiness. We need to know about the messiness, right? And so we need to come up with a model for the messiness. And the fact that we have all this data now means that we can come up with a data-based model for the messiness, all right? And then we can say, right, given that this is our data-based model for the messiness, which will be much larger than if we actually had a theory for what's going on, right? We can see, can we constrain? And what you find is that you can constrain, that, it's messy, but it's not so messy that you can't come up with constraints. I've tried to come up with examples. I mean, one of the ones that I find fascinating is the fact that you can do hadronic physics, okay? That you can do hadronic physics with these, you do these collisions and you get these, the end products are just a huge mess. They're a huge mess, right? In principle, they're a huge mess. Okay, we know what the fundamental forces are, but structurally, they're a huge mess. Yes, you still are able to learn something quite fundamental from that. And I'm sure there are many other examples in the real world where you can do that. So I think my attitude is a bit what you're saying, that, we're getting so much data, the images are so great, we're going to go so much better, that these problems, we will understand them even better. But even if we we don't come up with a theory, a complete theory for them. We have enough data that we can, in some sense, model them. We can model what's going on based almost like a, how would you call it, a positivist model for them, right? and that's enough, right? That's enough. So
that's
anyway.
a good way to put it. Let me just also add very quickly that, you know, what the good thing that's going for it is the fact that if you look at many of the cosmological surveys that people are planning, it used to be that we had surveys that were for galaxy evolution, surveys for cosmology. They were much more niche things. Now they are joining. You see more and more that, you know, the same surveys that you're doing for cosmology, you are building into galaxy evolution also. So it's a part of the surveys that you have to understand the galaxy that you're looking for. So sorry, I don't want to take time away from the questions of the students.
I mean, one of the interesting aspects that I found working on this is there is already a lot of data, okay, and there are aspects of the data that people have never looked at, okay, and so you know, my collaborator Harry Desmond has this incredibly ability of going to existing surveys, and you know, we think of something, he says, oh, we can use this survey, and then we've got 10,000 galaxies with incredible images of exactly the one we want to do.
And you'll have 10 million in 5 years.
And in 5 years, it's just another order of magnitude, right? So it's quite remarkable. Okay.
So I have a follow-up question on Raul.
Yes.
Because, the Dark Survey is looking at something called splashback radius. Are you going to talk about this later, or maybe discussions?
No. I'm going to
postpone that for.
My lecture tomorrow is basically about what I talked in the meeting in December, in which I think is using black holes to study deviations from cosmological deviations from gravity. So that's going to be my focus. So that's my so I think large scale structure is today. Large scale structure is today. The questions are today.
But maybe you can mention the splashback radius in the discussions in the Q&A session.
I know what it is. I've never studied it in detail, so I don't have anything that informed to say about it.
Okay, so there are other questions in the chat.
Okay. Reggie. Hi, Professor. I want to ask about dark matter halos as well. What happens to its profile as one gets near to the center of a galaxy, black hole? Well, I mean, that's one of the things that we've been trying to understand observationally and numerically, and I don't think we have a complete answer. What we know is that it very much depends on various aspects of physics. It not only depends on gravitational physics, but it depends on baryonic physics as well. What could be the moderator particles for, Pablo asks, what could be the moderator particles for this fifth force? Well, in all the cases that I've considered, it's a scalar field, so it's a spin zero particle. But Beatrice Tucci, follow-up question related to Rogerio's one. Wouldn't non-universal gravity, as far as I understand, a gravity that only couples to a particular amount of components, be against the equivalence principle? It would, yes, it certainly would. And the question would we have detected it now? So that's an add-on to the question that you're saying. And you know, we have to. So imagine you've got something that couples to baryon, something that couples to dark matter. We'd have to be able to construct a dark matter object to see that it fell. That its geodesics would be different from baryonic. Zaccaria, there is a paper of Noller, Santoni, Trincerini that was updated 2 days before, scalar tensor cosmologies without screening. So how can we use what you talked about to prove this category of Horndeski probe this? Well, you can't, because they're non-screened. So what I just talked about was theories with screening, using these galaxy methods for probing theories with screening. Reggie, short follow-up. Can I say that dark matter is zero or approximately zero near the center since black hole is a vacuum solution? No, you can't. Okay. I'm going to have to go because I have to host a meeting in 2 minutes.
Thank you. Thank you very much.
I will see you at Q&A.
Okay. Thank you very much. And see you guys in half an hour for Chiara's lecture. Okay. So thank you.